Welcome to the 6th episode of our jet engine series. In this video, we'll pick up where we left right at the exit of the compressor, ready for our modeling of the combustor. Let's dive right in!
3, 2, 1, top.
3, 2, 1, half, the flight test engineering channel.
I'm thankful that you are on this journey about gas turbines with me. So far, we have covered a lot of ground and set up a solid foundation to build our model. And because of that, we can now combine the concepts and code for Combustor into a single video, and that's what we're going to do today. We start where we left off, with air exiting the compressor at station 3, and now we need to add enough energy in form of heat to make the turbine spin and drive the compressor and also generate some thrust forward, which is what we're interested in. As the air-fuel mixture burns in the combustor, it's not unreasonable to assume that very little heat is lost through the walls. And so we'll say that this process is adiabatic as well. And this will make our life much simpler with the equations, as well as if you compare how much heat escapes the combustor through the walls versus how much heat we add by burning the fuel here, it's really a small portion. I always like to be mindful of what's happening physically. In this case, we just want to add fuel to air and burn it in the combustor. Easy, right? Well, there are a few constraints here. Let's look at some of them. I have made the outside of the combustor transparent so that we can see what's going on inside with the liner. First, we can't have the flame extinguished, so the conditions need to be stable here. The flow is coming into the combustor with a velocity between 30 to 60 meters per second, which by itself is an order of magnitude faster than the flame speed. Think of a candle in the wind, except now that the combustor needs to maintain its flame all the way from sea level, takeoff, where the mass flow is very high, to idle at altitude. So there are widely different mass flows and pressures and temperatures. And in order to keep the flame alive, the main mechanism is to have recirculation and turbulence. Because when we have the hot gas being sent back, it will mix with the unburnt fuel and ignite it. So the idea is to have this recirculation. Typically, this is implemented with a swirler, which induces a vortex into the incoming airflow. Next, the fuel is atomized and injected to mix with the swirling air for a short period of time until it meets the flame front and ignites. And as the flame travels downstream, it is recirculated from the sides. That's effectively creating a feedback loop. Here we see the swirler introducing air into a small duct, where the fuel will also be injected. The purpose of this small duct is to pre-mix the fuel, and we can see how the vortex will generate a reversal in the flow, keeping the flame stable. Another parameter that we need to control is the fuel-to-air ratio. Too rich and it will not completely burn and will generate soot. You might say, but turbines operate on a lean side, generally with excess air. Yes, but what really matters here is residency time. Remember that aircraft engines need to be small, light, and compact. So the combustor has limited space, which leads to limited time to burn the mixture. On the other hand, too lean and the flame might extinguish. So there's a balance here, and the FADEC needs to take care of keeping the mixture within parameters. We also have problems with emissions. Too hot and we get NOx. So it is an intricate balance. There has been a lot of progress in combustion technology to cope with these restrictions, and the common solution here is to do combustion in stages, where there's one flame that ensures stability, and depending on the power setting of the regime, another flame will guarantee power output. On the channel's GitHub page, you can access the gas turbine propulsion repo, and inside there's the Turbojet subfolder, and in there you can find a copy of this notebook, episode 6. You can follow along right there, or if you want to copy it straight to your machine, you can just click on this button up here. Links in the description. Just to reinforce the assumption that we made that the combustor is going to have an adiabatic flow, meaning that we're not going to exchange heat with the environment. And looking at a few of the typical values that we're going to use here, the stoichiometric ratio for kerosene is about 15:1. But turbines operate in the range of 60:1 to 120:1. So this is definitely a lean burn. And the combustor control must account for all of these conditions in order to keep the flame stable, keep the emissions under control, keep the maximum temperature within limits, and still have high efficiency. So starting from the compressor exit, the flow velocity is brought down to about between 30 to 60 meters per second in the combustion chamber. And this is to avoid too much speed and blow out the flame, as we talked about. But also, this is seeking lower pressure losses. You see, this in fact is the main reason where there is pressure loss in the combustion, which is friction. The swirlers, tangential injectors, and all of the turbulence that is created end up dissipating a lot of energy in form of friction, leading to between 4 to 7% loss in this sense, which is a lot. It's not small. The other source of pressure loss is due to the rise in temperature, which brings down density, and since mass flow does not change, the flow velocity needs to increase. Now, to increase velocity, there must be a delta P pushing the fluid forward towards the exit. This is called fundamental pressure loss, but this value is considerably lower than the loss due to friction, in the order of 0.1 to 0.3%. And we will lump both losses together and write this as delta P over P, which is right there. And it's going to range between 4 and 7%, as we said. Another source of energy loss is the fact that some small portion of the fuel makes it through the combustor, either partially or completely unburned. And this is accounted for with the combustion efficiency factor, eta B, which is the ratio between the theoretical amount of fuel to reach the temperature rise over the actual fuel used. And how much energy does the fuel have? Notice that we have not touched on fuel heat value here, and because Cantera will take care of this for us. But typical kerosene LHV is around 43 megajoules per kilogram. Our model here will try to follow the physical aspects of a real engine. We'll add enough fuel to reach the fuel-air ratio that we talked about, something between 60 to 120:1. And we'll let Cantera figure out the final temperature of the mixture. Let's see how this is done in code. The first thing we need to do is append the combustor parameters to our engine. So let's roll back here to the top where we had the definitions. And just to remember, we had created a few dictionaries, the engine parameters dictionary that will carry the engine physical parameters, and then the engine performance dictionary, which will carry the performance parameters. And we already had populated a few values for the inlet and for the compressor, and now for the combustor. Eta B is the combustor efficiency as discussed, and refers to the amount of fuel that ends up unburned. These old engines used to have thick black smoke coming out in the back, so let's use a low value here, 0.09 for instance. What else? We have dP over P as discussed. This is the pressure loss across the combustor, mainly due to the swirling gas friction loss. Next up is going to be max F, which is the maximum air-fuel ratio, meaning the richest the mixture will get. In this case, it's equivalent to the 60:1 that we talked about. The minimum, or min F, is going to be the opposite, is the minimum. It's the leanest mixture, and it's equivalent to our 120:1. Notice that both max and minimum values are set to guarantee flame stability. V nominal is the nominal flow velocity. This ranges between, like we said, 30 to 60 meters per second, and we'll use something right in the middle. The good thing about keeping all of these parameters in dictionaries is that later we can export them to a file, and as a matter of fact, we can have several files, one for each engine, and run the same model. Now, we're going to break down the combustor in two parts. before we ask Cantera to carry out the fuel reaction, we need to set the initial conditions. We have the flow coming in from the compressor, so we know the conditions just before the combustor. But we saw that if we keep the velocity high, the flame will blow out. So we need first to slow down the flow, which will change pressure and temperature. And although the pressure loss, dP over P, occurs in reality along the combustor, for simplicity, we'll calculate it with the gas cold, meaning before the combustion. Let's create a dedicated function that will calculate the cold gas properties called iterate combustor. So let me unhide this cell here, which is this one. We pass in the incoming gas properties as our Cantera solution object, the nominal gas velocity that we want the combustion to happen, one that keeps the flame stable as we saw, the Mach number of the gas coming in, the dP over P pressure loss, and we give it a Cantera object to pass out the gas properties as well, just like we did with the other functions. And now we start with the loop control. By now, you can see that this is a pattern in engines. We'll need to iterate a few times to hone in on the gas properties, since everything is interdependent. We'll start our combustor function with the loop control. Tolerance for convergence, same thing that we saw before, which will be the maximum difference between the gas pressure and the calculated pressure. Then the usual max number of iterations, the convergence boolean, and the variable that will keep track of the number of iterations that we are at. We then start with calculating the gas properties for the gas coming in. So we, just like we did before again, we calculate the gamma in. We calculate the stagnation temperature in by using the Cantera gas that we're passing in, plus the gamma that we calculated and the Mach number that we were passing in. Remember, this is coming in from the compressor. And we also calculate the stagnation pressure, P0 in, for the gas coming in. Because we're modeling this as an adiabatic process, the stagnation temperature before combustion does not change. So we start there by making the input and output stagnation temperatures the same here. Remember that we're dealing with a cold gas. And the stagnation pressure will decrease since we will have that energy loss that we talked about. So we'll set it to a fraction of the pressure at the inlet as per our dP over P pressure loss parameter. That's right there. We are ready to run the loop here, and we will, of course, run the loop while it's not converged and the number of iterations are less than the maximum. The strategy is the same as before. First, we update the gas out properties with the temperature, which in this case is the same as the input, and the pressure, which is lower due to the loss that we just saw. Just take note here that we are iterating over the gas out variable. This will be important later when we actually burn the fuel. We then calculate the speed of sound for this condition, and then from the nominal gas speed and the speed of sound, we calculate the Mach number going out, which is M out here. Then we get the gamma, and finally we calculate the static temperature and pressure with these two lines here. We'll keep looping until the calculated static pressure out is within tolerance of the previously calculated value. And if it is, we stop and set convergence to true. If not, we add 1 to the loop counter until it reaches the maximum allowable, at which point we stop and print out a message saying that it's not converged. And we explicitly return the Mach number going out and the convergence flag. The gas properties, remember, are stored in the gas out object, so we can access that when the function returns as well. Remember, this is the cold gas, so we did not burn anything yet. All we did was slow down the gas and dissipate some energy, mainly due to friction loss, which results in pressure loss. We'll ask Cantera to burn the mixture outside of the function, as you see. Let me scroll down here to number 11. This is all the stuff that we had done before. And here we are. So in order to get the air-fuel ratio for the throttle position that we have set in the engine operating conditions, we can change the throttle setting, but remember all the limitations of our model, especially that we do not have a compressor map, as we saw. We need to interpolate throttle position linearly between the limits that we set for stable combustion. This is what we're doing here. When we take the maximum minus minimum times the throttle plus the minimum, as we have here. It's our linear interpolation. We call this variable phi, which is the fuel to air ratio we want to burn. So far, we have pure air in our combustor. You could check that by looking at the composition of the gas, for instance, gas 3.x. So we can check that. Let's create a cell here above and see what our gas 3.x has. And you can see that it's only air by these compositions here. Let's delete this and keep going. And now it's where the magic begins. We call Cantera's set equivalency ratio method with our gas, starting with the proportion between fuel and oxidizer, the phi that we talked about. Remember that the fuel has been defined in the beginning of the notebook as composition fuel. And if you go back and look, it will be a hydrocarbon with 12 carbons, which is our kerosene. The oxidizer is air, which we also defined in the beginning as well as composition air. And with that, Cantera can calculate the amount of fuel that needs to be added to the air in order to have the proportion that we set with phi in the molar basis. But it did not burn it yet. It just added both fuel and air together in this mixture. How much fuel? We can get this from Cantera by invoking the mixture fraction method using mass as basis. So if we go here to the end, we're going to set the masses, the basis to mass. And now that the fuel-air mixture is set, let's iterate on this code mixture and get the pressure and temperature before any oxidation. Let's call our function here. Note that we pass in the gas from station 3, which is composed of pure air. And for gas out, we pass station 4, for which we already added the fuel. Remember that in our cold gas function, we will iterate over the gas out object. This is why I called for you to take note a while back, because we are passing in gas out, which is already a fuel-air mixture. We are going to increase our precision and calculate the gas properties more closely to reality, gamma, enthalpy, density, and so forth. So we will call our function using the compressor exit as the input gas, the nominal velocity for the flow, the Mach number that we had at the exit of the compressor, the pressure loss over our combustion chamber or combustor, and the output gas at the exit of the combustor, which is going to be our gas at station 4. And if we have converged, then we assign the Mach number to our collection, and this time is going to be station 4. And usually it converges pretty fast. 3 to 4 iterations are enough. And just a quick recap, what do we have so far? We have fuel to air gas mixture at a slower speed with the combustor pressure loss applied. So now we burn it. In Cantera, this is really easy. Just run the equilibrate method at constant enthalpy and pressure. This will take in the mixture we had, and using the reaction mechanism we chose in our endodecan rights YAML file, it's going to run a rather complex solver using the Villers-Cruz-Smith, or VCS for short, minimization technique. This is advanced code, kindly made available here by the folks at Cantera, so thank you, kudos to them. This all in a one-liner. And this will essentially minimize the Gibbs free energy for all of the species that are created when burning our fuel. This is amazing. And this is what's really great about Python. We have access to really complex and advanced code that would otherwise only be available in a more complex language. If you want to dive into the details, Kantara's site is rich in documentation, and as always, the link is going to be in the description. And finally here, we store the gas properties in temperature, pressure, and composition in our collectors list. And what we do at this last portion here is that we are going to propagate the gas composition downstream, because now we have gas that is burned with fuel. So we propagate the composition of the gas to all of the stations downstream from station 5 onwards. That's what this loop is going to do. You can see that I ran this before, so there's a spoiler here to show that it converged in 3 iterations, but let me reset the kernel here and run again. So I'm going to run from this cell up, all above selected. And yeah, so you can see that it finished in converged in 3 iterations. So now let's print and plot the results. Oh yeah, look at the temperature rise. Notice on the diagram here that the pressure is lower than the pressure at the exit of the compressor. So we're losing pressure, which is normal. This is what we modeled. And if we look at the printout, it will be higher here if you look at the pressure. And you might say, oh, what's going on here? But this is static pressure. And if we take into account the difference in Mach numbers from station 3 to station 4, look at the Mach numbers here. It goes from 0.33 to 0.10. And if we calculate the stagnation pressures, you see that it will be lower at station 4. So you can try that as well. You get around 2.18 ATMs for pressure for station 3 and 2.05 for station 4. So let me just zoom out a little bit so that we can appreciate the graph here. And you can see that the entropy really rises as we burn the fuel. The pressure is lower. The temperature, of course, and the enthalpy rise absurdly, very, very much. And this is looking good to shape our Brayton cycle. Nice! We're getting closer. If you want a copy of this notebook, please visit the channel's GitHub page, and the link is going to be down below. Stay tuned for the next video where we will add the turbine. See you there!